That's why it's summation. So in place of summation, we can give some limit. It's I equal to 1 to n. Okay. So what will be the number of n? It depends on you how you divide the whole cross section. Okay. It may be 5, 6, 7, 8. It depends on you. Okay. So our intention is to find out the alpha. Okay. Our intention is to find out our expression for alpha. So what we have calculated here, that kinetic energy for the whole cross-sectional area by considering small elementary area we have determined here, that we have put equation number 1. Okay. Now if you want to find out the kinetic energy for the whole cross-sectional area, if you find out the whole cross-sectional area, kinetic energy of whole cross-section area, so the equation will be same, half into mass into velocity square, half mv square. Okay. So equation will be same, your half into mass into velocity square. Okay. Or velocity square. So mass, again we have already discussed its specific weight. Today my mouse is not working properly. Okay. So mass is nothing but your specific weight multiplied by area. So see, in previous case we have considered a small area del A. Now as we are considering the whole cross section, so we are going to consider the whole cross sectional area. Okay. Specific weight multiplied by whole cross sectional area multiplied by your specific weight multiplied by whole cross sectional area multiplied by your velocity. Okay. Okay, that is your weight. Okay. If you want to find out mass, we have to divide by acceleration due to gravity. Okay. So this will be your mass for the whole cross sectional area. Okay. This will be your mass for whole cross sectional area. So this is what your mass. Okay. As this velocity is not constant, then we multiply this coefficient called alpha. Okay. And our intention is to find out the expression for this alpha. Okay. So in place of mass, we have substituted this whole expression, that is specific weight multiplied by area multiplied by velocity divided by acceleration due to gravity. Okay. And as because of this velocity, we have multiplied by a coefficient called alpha. Okay. And then we are taking kinetic energy, so half is there, that is why divided by 2, and it's v square. Okay. So if you further simplify, it will be alpha specific weight area v cube. This is v square and we have another v here, so that is why it's v cube divided by twice g. Okay. And this is your equation number 2. Okay. If you consider this one, this is equation 1 and this is equation 2. Okay. Okay. So next we are equating both the equations at 1 and 2. Okay. So here this is for kinetic energy for whole cross sectional area. Here also it is kinetic energy for whole cross section area, but it's depending on the small elementary area that we have considered. Okay, so that summation or that integration is same, so we can replace the summation by integration. Okay, so here the specific weight and this specific weight will be cancelled out. Okay, this specific weight and this specific will be cancelled out. Twice z and twice z will be cancelled out. Okay, and if you consider this alpha, it will be summation will be having this b cube and then del a. Okay, divided by this b cube by whole cross sectional area. Okay, and then this summation we have replaced by your integration. Okay, this is v cube del a, we have written dA divided by v cube a. Okay, so if you do further simplification, it will be small v by capital V whole cube dA by a. Okay, for example, for example, it's just for an example. Okay, this is your overall expression. Okay, now what we are going to do, we are going to consider a rectangular channel. Okay, and we find out the expression for rectangular channel. Okay, this expression is irrespective of the channel shape. Okay, now whatever we are going to derive, this is for only for rectangular channel. Okay, we are going to use this equation only. Okay, for a rectangular channel, we consider the depth of flow, total depth of flow is y naught. Okay, it's y naught. Okay, so we have considered one elementary area inside that rectangular channel. Okay, and we consider the depth of flow for that particular elementary area is dy. Okay, is dy. Okay, and area for particular small elementary area is dA. Okay, so if you want to find out the whole cross sectional area, that is your capital A, so your capital A is nothing but your B into Y. Okay, we all know for a rectangular channel is B into Y. Width of the channel multiplied by your total depth. As we are going to consider the whole cross sectional area, so your width of the channel is B, width of the channel is B, width of the channel is B, and your depth of flow is Y naught. Okay, so this is your total area. And if you find out the small elementary area, that is del A, del A is nothing but your same width of the channel, as the width of the channel for that small elementary area and the whole cross section area will be same as it is a rectangular channel. Okay, so B into dy. Okay, B into dy, that area for that small elementary area. Okay, so now you substitute in this equation. Okay, alpha is equal to small v by capital V whole cube. In place of dA, that is area for that small area that we have considered, it will be B multiplied by dy. Okay, and divided by, we have a cross sectional area, whole cross sectional area, that is nothing but B into y naught. Okay, then this BB will be cancel out, that is width of the channel cancel out. What will be left out is by capital V whole cube y by y naught dy. Okay, so and this limit we have already discussed that if this is width of the channel, sorry, the depth of the flow is 5 meter. If the depth of this 5 meter, then if you take 1 meter section, 1 meter section, it will be 5. Okay, So depending on how you are divided, but the ultimate or maximum limit is 5. Okay, your depth cannot be greater than 5 for that particular small elementary area. So that is why we have a limit from 0 to y naught. Okay, as y naught is the maximum depth. We are integrating with respect to y, so dy, and your limit should be from 0 to that maximum is, if it is 5, then it will be 5. Okay, so that is why your maximum limit is y naught. You have followed, na? Or if you have any doubts, you can ask me now regarding this derivation of your energy coefficient alpha. To find out mass, okay, so we know weight is equal to mass, okay, mass into acceleration due to gravity. Okay, mass multiplied by acceleration due to gravity. Okay, so first we are going to determine weight. Okay, so suppose if you consider a cross section, if that cross section area is capital A and velocity in that particular cross section is v. Okay, so what will be your weight? Weight will be is nothing but you have to take specific weight, that is rho into g. Okay, specific weight, then you have to multiply it by the whole cross sectional area. Okay, whole cross section area, then you have to multiply it by your velocity, that is your weight. Okay, and if you see, our aim is to find out mass. Okay, mass will be your, mass is nothing but your weight by gravity. Okay, from this equation you can say mass is nothing but weight by gravity. So if you divide this thing by acceleration due to gravity, you will get mass. Okay, so we definitely, for first we have to find out the weight. Weight is nothing but specific weight multiplied by cross sectional area multiplied by velocity. Okay, then if you divide this weight divided by acceleration due to gravity, you will get mass. And nothing but it's follow this equation. We all know weight is equal to mass into acceleration due to gravity. Okay, Any other doubts? Okay, we are going to proceed. Okay, so see, to find out alpha, we have this expression, or you can say this expression. Okay, this is your general expression, and this is only for rectangular channel. Okay, this is only for rectangular channel, and this is your general expression. Okay, irrespective of any shape. So here, if you see both the equation, we have small v, that is your average velocity for that particular small area. Okay, and that capital V is your average velocity for the whole cross sectional area. Okay, so to find out alpha, we have to first find out the average velocity. Okay, we if it is given, then it's okay. Otherwise, we have to calculate average velocity for the whole cross sectional area. Then only you can find out the alpha. Okay, so the whenever you have a numerical related to this energy coefficient, momentum coefficient, it mentioned or not, you have to first determine the average velocity. Okay, if it is given in the question that average velocity is this, then you need not to do, or you need not to calculate that average velocity. Or if it is not given, then you have to calculate average velocity at first, then only you can find out alpha value. So next topic, we are going to discuss the average velocity. The derivation for average velocity is similar to your alpha or energy coefficient that we have already discussed. Okay, here also, if this is your, you can see that figure number 1.7. In figure number 1.7, you can see this is our, you see this is a cross section of a channel where we have considered one small elementary area. This, okay, the area for the particular, we have considered del a dA. Okay, and depth of water for a particular small elementary area is d pi. Okay, and this small elementary area is y distance from the free surface. Okay, and the total depth of flow for the whole cross section is y naught. Okay, y naught is the maximum depth of flow. Okay, and now, okay, so here So maximum depth is y naught. Okay, and this is your velocity profile that we have already discussed. Here it is. Here this is your bottom of the channel. Here though we consider it zero, practically we have some velocity. Okay, but it's very difficult to find at the bottom of the channel, so we consider it to be zero. Okay, and then when we move upwards or towards the free surface, it increases, and because of the interaction between the air and the water, we have a decrease of velocity at the surface. Okay, so this is the small elementary area we are talking about, and the dy is the depth of flow for that particular area, and this elementary area is y distance from the free surface. Okay, so here we have to first consider the discharge. Okay, okay, so we know discharge is equal to area into velocity. Okay, area into velocity. Okay, we all know discharge is equal to area into velocity. So now we are going to find out the discharge for that particular area or small elementary area we have considered. So that area will be dq. Okay, and to find out the discharge for a particular small elementary area, we have to multiply it by area into velocity. So this small v is the velocity inside that area, and we are multiplying by del a. Okay, so we will get the del q discharge. Okay, so definitely in previous case we have calculate kinetic energy for a small elementary area, and then we have integrated or we have taken summation. Okay, to find out the whole kinetic energy for the whole cross sectional area. Okay, here also we have taken discharge, and then we have calculating the discharge for whole cross sectional area by taking summation. You can take here summation. Okay, in place of integration you consider summation v dA. Okay, so this summation again it depends on I equal to 1 to n. Okay, so that n, what will be the number of division, it depends on you. Okay, but the maximum limit will be your y naught. Okay, so you consider this is equation 1. Okay, so if you want to find out the discharge without considering that small elementary area, it is very simple. Discharge equal to area into velocity, where capital V is the average velocity and small a is the capital A is the cross sectional area of the particular section. Okay, so our intention is to find out the expression for this velocity. Okay, so this discharge and this discharge will be same, so that is why we equate both the equation. Okay, so here V equal to, definitely this will be in left right hand side, divided by A. We have A. Okay, that is why 1 by A V dA. So this is the equation for average velocity. Okay, so first we have to use this equation. We find out the average velocity, then we substitute in alpha equation to find out the alpha. So again we have taken an example of rectangular channel. Okay, so that total area will be B into Y naught. Okay, Y naught is the maximum depth of flow. That small particular area or small elementary area will be B into dy. Okay, dy is the depth of flow for that particular selected small area. Okay, y naught is the maximum depth of flow for the whole cross section. Okay, and width of the channel in both cases will be same as we are considering rectangular channel. Okay, now this equation will be your, first we have to set the limit, definitely from 0 to y naught, as y naught is the maximum depth of flow. Y naught will be the maximum depth of flow. So your limit is from, so that is why your maximum limit is y naught. Okay, so your limit will be 0 to y naught, then 1 by a is your capital A, so whole cross sectional. So that is why in place of capital A we are going to substitute b into y naught. Okay, then we have small v, and in place of your dA, in place of dA, in place of dA we are going to substitute area for selected small area. Okay, so dA is b into dy, so in place of dA we have substituted b into dy. So this b and this b will be cancelled out. Y naught, 1 by y naught, we bring it out, and what will be left out? Integration 0 to y naught b dy. Okay, v dy. Okay, so this is the expression for rectangular channel. Okay, this is the average velocity expression for rectangular channel. So we have to, if for the particular rectangle channel, if you need to find out the alpha value, first we have to find out the average velocity using this equation. Then we have to substitute this value in the alpha equation to calculate energy coefficient of that particular rectangular channel. So this meeting is going to end. Okay, so I think we have another class, so we will start the next class from 10:15.